So here's our experiment to look at the effects of ocean acidification on coral growth.
As the pH drops and the water becomes more acidic, there is less carbonate in the water.
The reason carbonate is important is because corals take calcium and carbonate and they make calcium carbonate, and they need that to make their skeletons.
We wanted to design an experiment that looked at the effects of ocean acidification on corals.
We are looking at how the lower pH affects the growth of the corals and whether or not it affects the dissolution of the coral skeletons.
There are two hypotheses. The first is a lower pH. There will also be a lower growth rate. And the second is a lower pH. There will also be a higher amount of dissolution of the coral skeleton.
We are going to have two tanks, like this one, and one of them is going to have just regular ocean water at a pH of about 8.1, and the other one is going to have ocean water, but it's going to be slightly more acidic, and it's going to have a pH of 7.3. Okay, we have our two tanks here, right here, and this one is our control tank. This doesn't have, it has the normal pH of the ocean. And this one we are going to put in hydrochloric acid to make the pH lower.
So you can't expose coral tissue to air. So what we need to do in transferring the corals, you actually have to keep them submerged at all times. It's a little frustrating. So what you do is you take a smaller size bucket and you actually submerge it in the larger bucket, scooping up the corals and water at the same time, and then put them into the experimental tank.
So now we have to weigh our corals every 2 days for the next 2 weeks. We do that by using this. It's a scale with a hook in the water, so that allows us to measure them in the water. You take the little tubes the corals are in, and you hook them onto the hook that's in the water. 4.492.
This process is being done with the live corals right now, and we're also going to repeat the same process, but with doing it with the dead coral skeletons, and we're going to see how much dissolution takes place.
These experiments are going to run for 2 weeks, and at the end we'll let you know the results.
The big question, I mean, with the effects of ocean acidification on marine calcifiers is what will the consequences be ecologically? But there are other results showing that other processes that are important in the life cycle are affected. One of those things is recruitment.
Okay, so corals reproduce via little larvae, which means that they have what's called a biparrot life cycle. They have a sedentary adult stage, which is the coral that we see, looks like a rock attached to the reef, but they also have a little larval stage. The larva then spends a dispersive period in the open ocean, and then it will come back and it will settle onto the reef. As it settles, within a few hours it starts to lay down a little calcium carbonate skeleton. When it actually then grows a little bit more, it becomes part of the reef community, and that's when we call it a recruit. So we're studying how ocean acidification is affecting this recruitment process. What we've been seeing is the fact that coral larvae that are trying to grow under these most acidified conditions, and what we'll possibly see in the world's oceans in 2100, are growing very slowly and are producing a weak skeleton. If these little corals after a week or 2 weeks are not able to put a solid skeleton down or grow upwards, they're going to face all sorts of problems. It's really a very vulnerable stage anyway on the reef. So without this problem of not being able to grow very fast, these tiny little corals, 0.5 millimeter in diameter, will easily get eaten by a parrotfish coming along and trying to get some algae next to the coral.
The parrotfish are really the lawnmowers of the reef, so they're the guys that are keeping all of the algae in check. But some parrotfish, it seems, are so kind of zealous in doing it that they're actually scraping off some of the rocks, some of the coral polyps. And they've done the math. Some of the big blue parrotfish can process a ton of rock a year, so they're really ingesting a bit of the coral. So what we're going to do is follow around parrotfish as long as we can and just count how often they bite.
We saw like a good 15 in a school, but you know, we could only count one, so it was hard, you know, zooming in on one of them if there's the old schooling in about good 15 of them, but we can't manage.
As you just seen, we've been out at the coral reefs and we've been observing the grazing of different types of fish and counting their bites at fish such as parrotfish and blue tangs. And we're really just looking at how grazing is going to negatively or positively affect the reef.
I saw one fish, like he was really biting at it. He would go down and he found a piece and he was like clamped onto it and was kind of pulling it up. Like they were really biting at the coral.
Yeah, so we guess the question is whether in maintaining the reef, the grazing is going to decrease the coral that can regrow because they're biting at the adult coral, or whether they're grazing on algae is just going to make new space for the baby coral to regrow. So it all depends. We're waiting to see how the grazing will affect the coral reef's growth.
MC cubed. Okay, let's check back, see how they got on with the coral growth experiment.
In this tank, we have the corals, which in the water is pH is 8.1. And this tank, the corals are growing and they're happy. In this tank, the water pH is 7.3, which is more acidic. And the corals they're not growing, and the skeletons are actually decreasing.
In conclusion, we found in the acidic water that the corals have trouble to grow, and their skeletons are being dissolved in the water.
We know for sure they grow slower, and as you grow slower, you have a more difficult time competing for space. And space on the coral reef or in any ecosystem is very important.
The best thing a coral can do is get big fast. And so the faster it grows, the more competitive it's going to be. So the fact that the growth rate is reduced, they're still growing, but at a very, very low rate, and also the fact that the skeleton is very weak, means that they're not going to be able to survive any other competitive interaction with anything, whether it be algae or whether it be fish or anything on the reef.
You may reach a point where the rate of accumulation of calcium carbonate and the growth of the reefs becomes negative. So rather than a growing reef, you may have a reef that is, for every year, is disappearing, is losing calcium carbonate.
If the corals are increasing and growing upwards, then they're also trapping sediment and they're basically building the island up, if you like. That's the best way to think of it. So as the corals grow up, the island is building up. And so at the same time, what we're seeing is we're in an age of sea level rise. So as the sea level is rising, as long as the corals keep growing upwards, then they're going to counteract the level of the sea rise is increasing. If the corals can't grow up at the rate of sea level rise, then you're going to see erosion of the land. So the corals are going to get eroded. This is then going to cause erosion of the land area, and so this could cause areas of Bermuda's coastline to be eroded away.
Bermuda is, the most northern reef that we have in the Atlantic. Because of this high northerly location, the carbonate ion concentration in the water is already pretty low in Bermuda. So Bermuda is one of the places where the effects of ocean acidification and low carbonate ion concentrations will be felt first.
We could start seeing the impacts of this in the next 100 years. So I don't think this should be seen as something which is going to occur a long time away. We're definitely already seeing the impacts of reduced calcification on corals.
Well, that's pretty worrying stuff. As you know, the coral reefs have actually formed Bermuda. They create the rock, trap the sand, and over time, over thousands of years, that sand becomes the limestone of Bermuda. Well, it's inside that limestone that we're going to explore next, deep inside the caves of Bermuda.